Hello and welcome. In this video we're going to investigate what's known as Euler's method. And we've already looked at some approaches for solving differential equations, including separation of variables, and we've looked at qualitative techniques that help us investigate or understand the solution of the differential equation without actually having to solve it. Now, oftentimes we're doing these things because the differential equation is not solvable, or because we just want some simple information without too much detail. So we can resort to things like slope fields, get a good sense of how the solution behaves. We can do an equilibrium analysis. However, perhaps what we want is some numbers. We want some values of y for different times. So let's think about this fact. In order to generate actual pairs or estimates of pairs that would be on the solution function, so let's imagine that for the moment we basically know what our initial condition is at time 0. So we have some 0 comma y of 0 ordered pair. We know that value, and what we want to do is maybe the exact solution looks like this. But what we want to do is we want to generate some estimates at different points in time. So maybe we use some technique and we estimate an ordered pair that is there. Now clearly that's not on the actual solution curve, but it is an estimate. And then at the next time value I estimate another one, and perhaps what I find is that my estimates are off, but they give me a sense of data. They give me the ability to manipulate some numbers. So maybe these are my estimates. And from those estimates, I want to get a sense of how this actual solution, y of t, behaves. And we can use this idea to generate estimates for these different pairs for some interval of t. So maybe typically we want to go from time 0, in this case, up to time, looks like time 3. We wanted to estimate the y value at time 3. Thus, we're utilizing what's called a numerical method. And a numerical method is just a method that gives you actual estimates of the solution. Qualitative method did not do this. It told us how the solution behaved. The slope field showed us how the solution flowed, where it went, whether it increased or decreased for different initial conditions. But we have yet to actually approximate solution values. So we're not going to actually build the solution function. We're going to build a bunch of ordered pairs that we hope to be very close to that function. To exploit this fact, let's start off with this ELK model. We have the rate of ELK per year being 20% of the number of ELK, so that's our reproduction rate. Another way of thinking about this is each adult female ELK produces, or every adult ELK on average produces 0.2 ELK as offspring. We can create a table like the one below. We can calculate the slope at each point, and we can then use these slopes to predict the next value of y. Suppose our initial condition is a y of 0 equals 10. So we can see that if we have 10 ELK, the rate of change of ELK per year is going to be 2. And in this table down here, we can see that more clearly. So we have in our first row, we're recording that at time 0, there were 10 ELK. That's a given. We need that information, along with how the rate of change of ELK occurs. And that's at a rate of 20% of the current number of ELK. So at time 0, when there are 10 ELK, this equation only relies on the value of y. It doesn't matter whether it's 1998 or 2025. 20% of the 10 comes out to 2 ELK per year. Now that's a positive number, and we should really make note of the fact that that's a positive number, because that tells us that the number of ELK is bound to increase by 2 ELK per year. Now this could be thousands or hundreds of ELK. So what happens here is 1 year passes. And since 1 year passes, and we're saying that according to our current information, we expect to gain 2 ELK over the course of 1 year. This is always going to be in units of ELK per 1 unit of time, or units of y per 1 unit of time. And the reason that is because if you put this over 1, now that's the numerator represents how many ELK, which is 10, per 1 year. So 1 year passes, which means I should gain 2 elk. So I started off with these 10 elk. I've gained 2 more over the course of that passing of 1 year. Therefore, now I have 12 elk. I can repeat this process now. So now I've come up with an estimate of the number of elk at time t equals 1. Okay, so at t equals 0, we said that there were 10 elk. Maybe I'll count in fives. 5, 10, 15, 20. So there were, at time 0, 10 elk. Now I assumed that 2 elk per year is a constant rate of change. So to get 12 elk right here, what I should draw between these 2 points is a straight line. And the reason I'm doing that is because this 2 elk per year is assuming a constant rate of change over the period of that full year. Now that is a simple way of thinking about it, but it also poses the problem of, doesn't the rate of change continuously? And when we're dealing with calculus, we know that the rate of change is just instantaneous, but we're treating it as if it were constant. So we just went from knowing the point 0, 10, and we just estimated the point 0, 12. I'm sorry, not 0, 12, but 1, 12. 1, comma 12. That's our new data value. So we're building points on this solution. Now, this is going to be wrong because inherently we just assumed a constant rate of change for any period of time. And for any period of time, the rate of change is not actually constant. So the new dy dt is now going to be bigger because now there are more elk reproducing. And so 20% of 12 is going to give me 2.4. And we're not going to round that. We're just going to assume this could be hundreds of elk, millions of elk per year, whatever. So now 1 more year passes. We get plus 1 year. And we expect to have 2.4 more elk if 1 year passes, and it did. So we have the original 12 elk from time 1, plus the gain in elk of 2.4, which gives me 14.4 elk. And now I'm going to repeat this process. Now here we are at time 2. Okay, so time 2, we now have 14.4 elk. So a little bit greater of a jump. Notice that our rate of change got bigger. So now this line segment is a little bit steeper. And this point here is the point 2, comma, move it over a little bit. Let's clean this up just a tad. So this was 1, comma, 12. And now we're up here at, right about there, 2 and 14.4. And now we can again compute the new rate of change, which again is going to be bigger because now we have more elk reproducing. And 20% of 14.4 comes out to 2.88. And the more decimal places we keep, obviously the more precision we have. But the same kind of notion moves on, that now we're going to add that to 14.4, and we'll have 17.28 elk. So at time 3, we now are up here at 17.28. Notice that rate of change, I'm exaggerating this, but it got bigger. And now we're at time 3, and we have 17.28 elk. We repeat the same process one more time because we want to estimate how many elk there are at time 4. So we'll take 20% of 17.28. And 20% of 17.28 is about 3.46. So notice again our rate of change jumped, and now if we take how many elk we had at time 3, plus the fact that we expect to gain 3.46 more elk, that's going to give us 20.74. 20.74. And so at time 4, we're up here at 20.74. And so now we have our estimate at time 4. We would say that we expect that at time 4 we will have 20.74 elk. And there is our estimate. Now, how good of an estimate is that? We don't know right off the bat, but fortunately for us, we know that this is a separable differential equation, and we can go about solving that. So the actual solution that we'll get is 10e to the 0.2t. So you can go ahead and try to do the separation of variables on that, see that that's what you get. and below are the actual values of y. So the thing that we notice about our estimates is that, first of all, here initially, if we compare time 0, those are the same, because that's a given, so that's not anything we're estimating. At time 1, we estimated 12 elk, but in actuality there were 12.21. This is the disadvantage of assuming a constant rate of change, because the rate of change is actually getting increasingly larger. So if we looked at time 1/2, it would no longer be a rate of change of 2 elk per year. It would probably be somewhere along the lines of 2.2 elk per year. So at time 2, we estimated 14.4. The actual value is 14.92. So notice that not only do we still have error, but the error just got bigger, because we were off by 0.21 at time 1, but at time 2 we're off by 0.52. And time 3 we estimated 17.28, but the actual answer was 18.22. So we were off by about 0.94 elk. And then by time 4 you can see we're approaching about 1.5 elk off. So we underestimated all the way up until time 4 compared to the actual solution. And one of the things we should keep in the back of our minds is we often don't have the actual solution to compare this to, so we're going to have to figure out how do we know that we're close with this estimation approach.